Hello everyone, welcome to your chapter 2 of this biology class. This part of the biology class will be dealing with the chemistry of life. So don't worry, there's not a lot of hard chemistry or anything like that, but we can avoid it. Everything that's around us, just think about what you're breathing, the oxygen you're breathing in, the ground you're standing in, and the water or the drinks you had this morning is made of something. It's made of matter. And in order to understand what matter is, in order to understand what cells are and what they do, we need to have a basic understanding of the different phases of matter. So, for starters, we know that matter is made of atoms. So the atom is the smallest part of any matter. But these atoms are made of particles. So when you think of an atom, you need to think about 3 different types of particles that are making this atom. And we need to think about neutrons, protons, and electrons. And we will address this a little bit later. Now, the other thing that we need to understand is that matter comes in different forms. So we know that on Earth, there are mainly 3 phases of matter. So what do we have? Well, we have liquid, right? Just think about water. So in this chapter, we'll be talking a lot about water because water is super, super important. Now coming back to the phases, we know that water can exist as a liquid form, right? So this is no mystery to anyone. We all have seen water, we know what it looks like. And we know that between 0 degrees and say 100 degrees, this water usually exists in liquid form. So at 0 degrees, it's a mix of ice, so solid and liquid. But as the temperature gets higher and higher and higher, by 80, 90 degrees to 100, we see that water starts to boil. And why does it boil? Well, it boils because it's transforming itself into another phase, and that other phase, of course, is gas, right? So we know that water exists as a liquid. It also exists as a solid, and sometimes the 2 of them can coexist together. And we also know that water can exist in gas form, which is water vapor or steam, for example. So when you are boiling water and you see these bubbles coming up, well, that's a transformation from liquid to a gas form. So we need to address these issues because as we go on in this course, and especially the next chapter, we will explore the different molecules that are their cells and everything that you know in nature are made of. So we will look at different types of lipids and sugars and all of that. But of course, the goal here is certainly not to address this at this moment, but we will later. So this chapter mostly deals with the way atoms are made, right? So what do we find? When you look at an atom, what do you find there, right? So we will look at those particles. We will look at the periodic table. We will see how the different types of atoms are classified and grouped together. The periodic table makes a lot of sense when you know what to look for. We will also explore the properties of water, and so not just the phases as liquid, solid, or gas, but we will see that water is a very, very special molecule, and we look at the different properties of water. So I really hope you enjoy this chapter. It's a very important chapter. It's the beginning of a fantastic journey, I think, in biology, and I really want you to grasp all the different pieces of that chapter. So without further ado, we will start this chapter right away. Thank you. We're going to talk about the chemistry of life. So please don't be worried about it. Chemistry, some of you don't have any exposure to chemistry. That's fine. We're going to look at the very basic of what we need to get in order to understand what's coming after that.
So as we will go on over the next few chapters, we're going to talk about cells, we're going to talk about different molecules and everything. And we will understand that cells are made of different molecules. And molecules, well, we need to know what a molecule is. In order to understand what a molecule is, we need to get to the basic building block of what a molecule is. And that small building block is something that we call the atom, right? So A-T-O-M, an atom. I'm sure all of you have heard about atoms, what they, maybe you don't know, or maybe it's a concept you're not sure about what that is, but the atom is a very, very small piece of a molecule. So if you can think of a Lego piece, a house or a wall or an airplane or whatever, when you look at your construction, Lego construction, you have something, a shape, a form that you can, you know, play with, build on, and everything. Well, that would be the molecule. Well, every single Lego block would be an atom. So, what are atoms? Well, atoms are made of something else, right? So, matter, no matter what it is, so it can be gas around you, the ground your feet are on right now, the surface of this board, or whatever, this camera that I'm shooting this video with, is always made of something, right? So that something is made of molecules, the molecules are made of atoms. The atoms, we can even subdivide the atoms into smaller pieces. And the basic building blocks of the atoms are known to be particles. Now, one thing that I am not going to go to is to fraction those little particles even smaller, because it is possible to do that. Of course, I'm no expert in that field, so I will stay away from that. But I just wanted you to know that it's very, very possible to go smaller and smaller and smaller and smaller and super small subunits. What I want us to concentrate on is the basic building blocks of what atoms are, and namely what we do have in when you're thinking of atoms, you're thinking of something called electrons. Electrons, we're thinking about something else that's called neutrons, and also another part that's called a proton. Now, one thing that I need to tell you is that electrons have a negative charge attached to them, and protons have a positive charge attached to them. Now, when you're thinking of an electron, when you're thinking of a neutron, the neutron is called neutron because it's neutral. It has no charge whatsoever attached to it. Okay, so that's an important piece here. Now, when we're looking at the structure of an atom, we know that there are two parts of that. And the first part is something that we call the nucleus. Okay, so we would have something like this, so in the middle of it we have something that we would call the nucleus here, and then around that we have electrons. So I'm just drawing an electron here, just one, but there can be many, many of those electrons. So I'm just getting here as simple as possible. We can complicate this a lot more, and I don't want to do that. So we have the nucleus that's on the inside, and then we have on the outside of the periphery, we have the electron, or electrons if there's more than one. Now, one thing that I want you to know is that the nucleus is made of two particles. First one is the neutron, so let's draw like a circle like this for the neutron, and then we have the proton there, right? So that is still the nucleus. So what we have here is still, right here, the nucleus. And then the electron is still at the periphery, right? So you can think of the Earth and the Moon orbiting the Earth, right? So that's what the electron does. Now, what I just told you is just an image for you to understand where the electron would be relative to what the nucleus is. The nucleus is made of protons and neutrons, okay? So this is just an image. The one thing that I really don't want you to stick on, I don't want you to think of this analogy as the absolute truth, is that I don't want you to think that the electron is spinning over and over and over again around the nucleus. The electron, it has been demonstrated over and over and over again that the electron is not there and just spinning around the nucleus. The electron is somewhere in this area around the nucleus. It's not spinning around it just like the moon would spin around the Earth. So that's a very important thing here to understand. So I'm going to erase this here and draw something that's probably more accurate of what an atom would look like. So let's go back to the nucleus. So in the nucleus we have the neutrons, and let's say I do have a proton there, right? And we know that the electron is somewhere around here. It's not spinning, but it's at the periphery. But the electron here is one thing that's important to understand is that the electron will be in different spots around this nucleus. So it could be here, it could be here, it could be here, it could be here, here, or here. You see, there's different spots where it can be. And it could be here, 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 here at any given time. Actually, it's impossible to know exactly where the electron is at any given time. But one thing that we do know is that the electron will spend some time in spaces that could look like this. And it will spend probably more time around here than it would spend here. Okay, so if you were able to take a picture of an atom and look where the electron is, you would see that most of the time the electron spends its time in a certain area than another one. It doesn't mean it can go there, it doesn't mean it cannot be here or here. It means that it usually spends more time here. Those parts here, these portions of the atom, or where the electron spends its time, they are called orbitals. Okay? So what it means is an area where the electron will spend some of its time. Exactly where in this area, we don't know. But we know that it's found in these pieces here. Okay? So that is a very, very important part of that. Now, what we have here is something that we call a neutral atom. So I just drew an atom for you here. We see there's 2 neutrons, there's 2 protons in plus, right? We know that this is the nucleus, and then I have 2 of my electrons right here, right? So what we have here, and the reason why I call this a neutral atom, is because there's no specific charge attached to it, right? So what you can see here is that if we understand that an electron is negatively charged, right? Negative charge. And then we have a positive charge at the proton. So if we have 2 positive charges and 2 negative charges, the net charge of this is 0, right? Because the positive charge will cancel the negative charge. So the net charge of this here would be something that's called 0. Well, not called 0. It is a charge of 0. Now, one thing that I want you to know it is possible for atoms to sometimes grab an electron from another atom that would be closer here. It is possible for this atom here to grab an atom, but it's also possible to lose an atom, right? So if this atom here grabbed an atom from some other atom, well, the other atom lost an electron. Right? So let's say that what we have here, let's say that this atom here grabs an electron, right? So it grabs an electron from a neighboring atom, right? So what we have here is we have 2 protons and we have 3 electrons. So you see, this is no longer neutral. This is no longer neutral. This is now charged. And the net charge is a negative. It's negative in this case here. In the other case, if we have this atom that loses one of its electrons, right? We're no longer in neutral zone here. What we have now is one more proton than we have electrons. And in that case, we would be not be in negative territory, but we would be positive in this case. Okay? So whenever an atom, and that's a very important concept here because you'll see this coming over and over and over again. So it's important to understand this concept. Is that whenever an atom that was a neutral atom loses or gains electrons, the charge of this atom will change, either positive if it loses an electron, or negative if it gains an electron, right? And in that case, when we have something that is either positive or negative, we will now call this an ion. Okay? So this is now an ion. It is an atom that has lost or gained electrons. It has a charge, a net charge to it, and it is now called an ion.
Okay, so before we go a little bit further down in explaining the isotopes and what it means and everything, I think we need to stop for a few seconds here and explain what the periodic table of the elements is. So one thing that we agree, hopefully that we agree now, is that we know that matter is made of different atoms, and that atoms will combine in different combinations and form compounds, right? And these compounds eventually, if they're complex enough, they turn into molecules and all of that. So anyway, I don't want to get ahead here too much of talking about molecules, but I want to go back to the basics of what the elements are. So one thing that you need to know is that there are, as you can tell here, there are 92 naturally occurring elements on Earth, right? If you look at this table here, these are all the elements that are known to mankind, and there are more than 92 elements in this table. Well, one thing that's important to understand here is that there are 92 naturally occurring elements on Earth. However, we were able to synthesize many of those elements. Actually, when you look at this table here, there's 118 of them. So, and some of them have a very, very short life. It's only a few fractions of a fraction of a second, right? So anyway, the goal here is not to talk about those exceptions, but basically to give you a little bit of an understanding of what the periodic table of the elements is. So now, if we look a little bit closer to any of those elements, we will notice a few common things. So let's start with the first one, the first of the elements here, which is hydrogen, right? So we see that there's different groups, group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 18. And those groups here are further categorized in different, different categories, if I can say it like that, and some are known to be metals, some are transition metals, and etc., halogens and all of that. No need to get into this at the moment. One thing that I want to show though is this, right? So if we look at the first element here, so we look at hydrogen, and we have a few bits of information right here. So the first one is the atomic number, right? So if we look at the atomic number, we see that the atomic number for hydrogen is right here. So we have a number of 1. The symbol for hydrogen is H, right? So the atomic number means how many protons are found in the nucleus of this atom. So if we have an atomic number of 1, it means that we have 1 proton. If we have an atomic number of, say, 23 in the case of vanadium, right, we have 23 protons in the nucleus of this element. Now, when we look at the relative atomic mass for this atom, which is 1.01, so let's just forget a 0.01 here and just concentrate on the 1. The relative atomic mass, which is the number of stuff or material or elements, particles that we find in anything. In this case here, we have the relative mass of 1.01. So let's forget the 0.01. We have a mass of 1. What the relative atomic mass tells us is that it is the number of total particles we find in nucleus. So we know that we have an atomic number of 1. So we know for sure that in this nucleus we have 1 proton. But then if the atomic relative mass is 1, then it means there's nothing else but a proton in there. So let me give you another example so that you understand that a bit better, right? So we have been talking about sodium a little bit in this course, and we will talk a little bit more about it. So let's look at this one here. So sodium is here. The atomic number for sodium is 11, which means that there are 11 protons in the nucleus, right? But then when we look at this here, the sodium, right, we have the relative atomic mass of it, which is 22.99, so basically 23. What does that mean, right? So it means that the total number of particles that we have in sodium is basically 23. We have 11 of those particles that are protons. So the rest, in this case, 23, are neutrons. So we would have 12 neutrons for 11 protons in sodium.
So when we're looking at atoms, we need to understand that atoms are classified in categories, right? So we have seen the table of elements, periodic table of elements, and whenever we have an atom and that atom is neutral, we call that an element. So there's different elements, as we've seen in periodic table. So we can think of hydrogen, we can think of sodium and chlorine, we can think of oxygen and bromine, and we can think of tungsten and iron and nickel and all of that, right? So they're classified in different categories. Now, one thing that is important to understand is that there is vocabulary that's associated with this classification. And one of those terms that is important is known as the atomic number. So what I have here is an atom of carbon, right? So that's something that you would see in the periodic table of elements. And then you probably notice that when you look at the periodic table of elements, we have all the elements that are inside a box like that, and there is a number right here, okay? And that number right here is known to be the atomic number. The atomic number. So what does that mean? Well, that number here means that there are so it's number 6. That means there are six protons. We have 6 protons inside the nucleus. Okay, so that's why we have the atomic number here. If this is a neutral atom, how many electrons should we have? If it's neutral, right? Think about it for 2 seconds. 1, 2, yes, of course, we would have 6 electrons because it's neutral. Now, this number here doesn't tell you about the electrons. It tells you about the protons, but if we know that it's a neutral atom, the element, we know that there should be as many protons as there are electrons. So that's an important thing. Now, what I want you to know is that there is another number that is associated with this element right here, and that is called a mass number. Okay, and you need to understand this because we're going to get to a concept in just a few seconds, and it explains a term that comes over and over again. You'll hear this often if you pay attention. And that number is called the mass number. And the mass number is the number of protons and neutrons that we have. So basically it describes the nucleus, right? So for carbon, there is a mass number of 12. Now, notice that I said there is a mass number of 12. Actually, there's more than that. But let's not complicate things right now. The mass number is equal to the number of protons we have, the positive particles, plus the neutrons. Right? So if we have a mass number of 12, and we know that the atomic number tells us that there are 6 protons, then it's very easy to understand and to calculate how many neutrons there are, right? What we have is the mass number, and we subtract the atomic number from that, and then we get a number of neutrons, right? In this case, if it's 12, then, of course, we would have 6 protons and 6 neutrons, right? Quite easy. What I want you to understand is this, is that carbon is defined, so an atom of number, an atom is defined by the number of protons it has in the nucleus, and of course by the number of neutrons it has, okay? But it is possible for a carbon atom to have a different number of neutrons. So basically, we could have this. We could have this. We could have carbon, that's a symbol for carbon, has an atomic number of 6. And then it is possible for another atom of carbon to have the same atomic number. Now the example I just gave you is the mass number of 12. But get this, it is also possible for carbon to have a mass number of 14, right? So 6 here, we know that we have 6 plus 6, 6 protons, 6 neutrons. In this case here, because the atomic mass of that atom is 14, and we know we have 6 protons, in this case here, we would have 8 neutrons. Okay? So, you see what we have here is a variant of carbon. We know it's carbon. It has 6 protons. Of course, if it's neutral as an atom, it also has 6 electrons. So that's fine, we know that. But in one version of it, it has 6 neutrons, and the other one it has 8 neutrons. When we have atoms like this that vary by the atomic mass, we call these here isotopes. Isotopes. So, carbon 12 is an isotope of carbon. Carbon 14 is an isotope of carbon as well, right? And if you ever heard of carbon dating techniques, right? So when we find fossils and we want to date the fossil, we want to know, okay, it's been like 120,000 years ago. This part was a part of a rib of an animal or something like that, and we do carbon dating, what we do is we measure the number of carbon-14 there is. Many isotopes, not all of them, but many isotopes are radioactive, which means that the nucleus is unstable. It will at some point try to go back to carbon-12. I'm not going to get into the details of this, but I just wanted you to know that because you will hear this over and over again, and now that you're aware of it. So isotopes. Many atoms, many elements have different isotopes of them. So when you look at the periodic table of the elements, we see all of those symbols. We have potassium and sodium and the metals and all of that, right? Well, many of them have different versions of them, if I can say it like that. So these versions, the many variations that we have, they're not infinite variations. We have some variations, and these are called isotopes.